So this Asia Brewers Network technical series presentation is brought to you in partnership with Fermentis, experts in the art of fermentation. I'll now hand over to Krishna from Fermentis, who will be discussing the impact of the Lactobacillus species and its pitch rate on lactic and acetic acid production and other common flavour compounds. His presentation will include details on the souring process, the development of organic acids and flavour compounds, as well as how to obtain a balanced sourness in your beer. So Krishna, over to you.
Thank you so much, Charles. It's really amazing because in just like a couple of sentences, you managed to cover everything that we would be presenting today. So thank you everyone for joining us. I'm Krishna, and with my colleague Simon, we will be just talking about everything with regard to sour beer. So now, the main aspects that we're looking to touch upon today is the souring process, the lactic acid bacteria metabolism, that is homolactic and heterolactic fermentation, following which I pass it on to my colleague Simon, who will talk more with regard to what you can tweak to bring about different acids. Along with that, I'll give a quick talk with regard to the characterization studies that we have done, and finally we sum it up with the conclusions. So coming to the sour beer process, one of the main aspects that you have to remember is that there isn't anything different. You do end up going through the same process, that is milling, mashing, filtration, boiling, cooling, fermenting, maturing, and then at the end putting it into package. So if you're looking at something like using malt and wheat, you would end up post-cooling doing a mixed primary fermentation in an oak barrel. To give you an example of that, you'd be getting some of the more Belgian styles like the Lambics, the Gears, or the German Gers, where you're getting a mixed fermentation done in oak barrels or foeders. During fermentation, you can do your primary fermentation in your fermenter and then end up going through a mixed fermentation or a secondary fermentation followed by a prolonged maturation. For this, you would get styles like the Flanders Red Ale. Here, you have the beers aging for a really long time. And then post-cooling, you can do a mixed inoculation with yeast and lactobacillus, or you can also end up doing a secondary wherein you're again adding some more lactobacillus. So this is, to give an example of this, would be something like the Berliner Weiss. What happens in all these different styles is that you're adding your bacteria, or you're bringing in the souring culture post-cooling, and it's ended up adding it in your fermenter. What would happen with this is, in a modern brewery, is we try to isolate it and try to bring it about in such a way that we do not get a contamination. So keeping that in mind, the kettle souring process is one which is really good. So what you do is immediately post-filtration, your non-hopped wort is boiled. So we choose unhopped wort because hops have a bacteriostatic effect. The wort is cooled and you add your culture into that. It is kept until you're able to get the desired amount of acid production or pH, and then following that, you end up boiling it. Post-boiling, it is taken forward and you're able to get your different styles of sour beer. Coming to the metabolism, they can be broadly classified into two categories. One is homofermentative bacteria. So in homofermentative bacteria, you have your glucose molecule that is consumed by your bacteria to give you lactic acid. So an example of this is the Lactobacillus plantarum, or what we have launched as SAFSA LP652. The other method is the heterofermentative. So in the absence of alcohol, the bacteria is able to consume the glucose to give out trace quantities of ethanol and a lot more lactic acid. But if you do end up adding oxygen, you get it into two very defined metabolic pathways wherein you get acetic acid and you get lactic acid. We have launched a new strain for this called LB1 or Levi Lactobacillus brevis 1. To talk a little bit more about this, I pass it on to my colleague Simon. Simon, over to you.
Thank you, Krishna. Thank you very much for this first introduction. So normally you should be able to see my screen at the moment.
Yes.
So thank you. So as you just introduced at Fermentis, we've got now two strains, one being Homofermentative, the Lactobacillus plantarum, LP652, and the other one being heterofermentative, which is the Levi Lactobacillus brevis, the LB1. And as this webinar is called Ask Fermentis About Sours, also our R&D, whenever we launch a new product, our R&D is asking a lot of questions to the new microorganism we have on the market. So the few slides that I will present you now is an extensive characterization study on these two microorganisms that we have compared in different conditions in order for us to be able to better understand them and better advise you brewers to reach the targets that you want. So we have been looking at different things. First, we looked at different pitch rate. Then we looked at different densities of 8, 12, and 16 plateau. We looked at different temperatures of Kettle sour process from 30 to 45 degrees Celsius. And then finally, we looked at the anaerobic or aerobic condition. And throughout all of these trials, so under all different four conditions, we looked at the kinetic of acidification, and we looked at the organic acids that were produced by the two microorganisms. So first, I will present you the result for the pitching rate. We chose one single density of Wort, which is a 12-degree plateau, a 30 degrees Celsius for the Kettle souring temperature in anaerobic condition, and then we looked at different pitch rates. On the left, you have the results for LP652, so you have the curve of acidification over time, and you have the same curve on the right for the LB1. What we see is that already by using a very low pitch rate of 1 gram per hectoliters for both bacteria, we are already able to have the proper Kettle process. If you increase this pitch rate, you will, by doing so, increase the acidification, the kinetic of acidification, but also the final pH. You'll be able to lower the final pH that you will get throughout this Kettle souring process. If you compare the two microorganisms, so the LP652, the plantarum, and the LB1, the brevis, you can see that by using the LP652, you would be able to reach a lower pH. Then the second parameters we looked at is so still on the pitch rate, we looked now at the organic acid produced, because pH is one thing, but what is also interesting to know is what are the specific organic acids that are produced and leading to this decrease of pH. So again, here on the left, we have results for LP652, on the right for LB1. And we looked at the lactic acid produced and the acetic acid produced under different pitch rates. For LP652, you see a clear increase of acidification, of lactic acid production by using a higher pitch rate. There is almost no production of acetic acid. Whereas for LB1, you also observe an increase of lactic acid production throughout the increase of pitch rate, but it is lower in comparison with LP652. However, you have a higher production of acetic acid. This being in anaerobic condition, you will see that by playing with the oxygen, you can even increase this acetic acid produced. Then the second parameter we looked at is the density of your Wort before Kettle souring. So we looked at different pitch rates of 8, of 10, of 12, sorry, and 16 degree plateau. And here again, we have the curve of acidification, so the pH over time, with on the left LP652, on the right LB1. And what we can observe is that for between 8 plateau and 12 plateau, there's not much different in terms of acidification. For a particular bacteria, we would reach the same pH. At 16 plateau, interestingly, we see that the final pH is slightly higher in both cases. This is simply explained by the higher buffer effect that is preventing your pH from moving, from changing, because of the higher buffer effect in higher density wort. Again, if you compare the two, you're really able to reach a slightly lower pH by using LP652. Then we looked at the organic acids that were produced. And here again, similar as what we observed with an increase of pH rate, if you increase the density, you will slightly increase as well the final production of organic acids, which is mainly lactic acid for LP652, and for LB1, a mix of lactic and acetic acid. Then at the third variables, we looked at the temperature used during the kettle sour process. So from 30 degrees Celsius up to 45 degrees Celsius. What we have observed is that for these two strains, the best temperature, the best range of temperature for the kettle sour is between 30 and 37 degrees Celsius. What you can observe here with the orange curve and even more with the gray, use a temperature higher than 37 degrees Celsius, you're killing and inhibiting the bacteria and preventing it from doing a proper kettle sour. So at 40 degrees Celsius, you already see that there is less production of organic acid and therefore less pH decrease. And when you use a temperature of 45 degrees Celsius, you're just killing the bacteria and there is no kettle sour process at all. We can also observe this when we look specifically at the organic acid produced. So similarly at the curve we saw before on the pH, we see that 30 and 37 degrees Celsius are leading to good organic acid production and a good pH decrease, a good acidification. But when we start to have higher temperatures, such as 40 degrees Celsius, there is a decrease of this organic acid production. And when we reach a temperature of 45 degrees Celsius, there is no more acidification and no acidification at all, no organic acid production. So the last parameter we looked at, the last variable we wanted to answer is whether you should or you should not use oxygen and what would be the impact on your kinetic and or the organic acid production. So first on the acidification, we have here, again, the acidification curve, so the pH over time, with in blue, the curve with presence of oxygen, so with aeration, and in brown, without oxygen. And what we see here is that for the Lactobacillus plantarum LP652, by using oxygen, you will slightly decrease the acidification, so you have slightly higher pH. And you observe the same thing for LB1, but with less impact. But more or less, you will get slightly improved lactic fermentation by using oxygen for LP652. Here we are looking at the details on the organic acid produced. So on the left, we have the lactic acid and then the acetic acid. And then the ratio L on A is the ratio of lactic acid over acetic acid, which is interesting in from a brewer point of view. If you want to balance the acidity of your kettle sour process, to balance a little bit the sourness that you will be perceiving in your beer, in your final products. So if we look first at the LP652 results, so the big bar in blue, we see that without oxygen, there is a huge production of lactic acid, as we have seen before, almost no production of acetic acid. If we add oxygen, there is slightly lower production of lactic acid, but still very, very significant. And more interestingly, if we look at the LB1 without oxygen, so that is the orange bar on the left, the second orange bar on the left, we see that there is, in comparison with LP652, there is less production of lactic acid, but there is also production of acetic acid. But then if you add oxygen for this Lactobacillus brevis, very interestingly, you will slightly decrease the production of lactic acid, but very much increase the production of acetic acid, and therefore influence the ratio of lactic acid over acetic acid, which is, on an organoleptic point of view, very, very interesting. So on the conclusions for this characterization study on the kinetic and on the organic acid produced, what we can say about these two strains is that they have common features, common characteristics, such as the fact that acidification kinetic, no matter condition that you would be using, is pretty much equivalent. There is also no significant impact of the wort density on the lactic fermentation. And for both strains, the optimal temperature is between 30 and 37 degrees Celsius. Then on the main differences between these two strains, if you want to create different sour beer, we have observed that LP652 produces more lactic acid in all conditions, and LB1 produces also more acetic acid in every condition. And even more, in presence of oxygen, you will strongly increase the acetic acid production by the LB1 strain, which is the brevis bacteria. This being said, I will hand it back to Krishna, who will talk a little bit more about the sour beer characterization and the organoleptic profiles of the beers we can produce with these two strains.
Thank you for that, Simon. So just starting from where Simon left off. So Simon has given us some really, really interesting information as to how you could play around and change your ratio of lactic to acetic acid. But how does this play out in terms of when you add yeast into the mix? So for this, similar to a lot of studies that we have done, we started by first taking 100% Pilsner malt base, and we went in with a souring process wherein we used both the cultures at 10 grams per hectoliter, did the souring at 30 degrees Celsius. The wort was at 12-degree plateau in an aerobic condition, and it was allowed to drop all the way down to pH of 3.5. So one thing that you have to remember is that we started with the wort pH of between approximately 5.2 to 5.5. The final pH of LB1 was 3.5, although not that low with previous trials, because the wort in this condition was very, very different. So taking this, after that, we ended up taking this acidified wort and pitched yeast into it at 50 grams per hectoliter. We took ale strains which were POF positive, POF negative. POF stands for phenolic or flavor positive. So we took ale strains that could give out phenols, wouldn't give out phenols, and we also added lager strains. All of them were fermented out at 23 degrees Celsius. And before I forget, the wort was acidified to 20 IBUs. Following this, we looked at some of the more important aspects, that is the fermentation performance. Was the yeast able to handle this pH? And then a sensory analysis, what did people feel about it? And then look at a more chemical aspect of it by looking at the aromatic components. So looking at the ale strains, that is both which are POF positive and POF negative, for the POF negative strains, we use K97, S33, SO4, BE256, and the most commonly used strain, USO5. In POF positive, we use all our three strains, B134, T58, and WBO6. As you can see, K97 per se was not impacted at all, or very marginal impact was there in the acidified wort, which was acidified with LB1 and LP652. But when you consider USO5, when compared to a control which hadn't been acidified, we see that wort that's been acidified with LB1 has a much more negative impact when compared to the control in terms of rate of fermentation. When compared with the wort that was acidified by LP652, probably we could say that USO5 is slightly more susceptible to acetic acid when compared to lactic acid. When we compare it with the lager strains, we found this actually very different, because you could see that LB1 and the control, the wort that was acidified by LB1 when compared to the control, which had been acidified and fermented out with S23, nearly overlapped. There was absolutely no difference. Whereas with LP652, we saw that there was a slight lag, but at the end of the day, the fermentation continued and both the endpoint was the same. When we compare the apparent degree of fermentation of all strains, we can see that there is a negligible, very, very minor impact. In some strains like B134, you can see LP652 has a much bigger impact when compared to LP1, but when compared to that, we could treat as an outlier. But when we look at it compared to all the other strains, there was no significant difference at all. Now, looking at it from a sensory perspective, here you can see that when we look at the curve of S33, you can see that LB1 has a more rounded curve, wherein it is fruity with a little bit of, with a marginal amount of sweetness. Whereas with the LP652 wort is more one-dimensional, one-directional, and it tends to enhance the acidity a lot more. So what people could pick up more is the more citrus character coming through more strongly in this. When we considered it with a POF positive yeast strain, that is the wort that had been acidified and then fermented with a POF positive yeast strain, we were able to see that with LB1, there was a strong phenolic odor with an overall well-rounded phenolic flavor, fruity flavor, marginal sweetness, and not very much in terms of the alcohols. And now this is what I find really interesting, as you'll see the next, is that with LP652, the entire phenolic character was nullified. So even though the wort was fermented with a POF positive yeast strain, LP652 was able to do something that ended up nullifying the entire phenolic character, enhancing the fruity flavor, the acidity, especially the fruity odor. One notable aspect that was mentioned by all the tasters is that when they were trying it, people did they noticed an increased drinkability was seen in the beer that was produced in conjunction with LB1. This is probably due to the mixture of organic acids. So we could see that even a POF positive strain was made POF negative in its sensory due to LP652. So this is just a quick sum up of all the points that I've mentioned. So a low phenolic perception for POF positive yeast strains when we have done it with LP652. LB1 as a strain respects the phenolic character. The acidity perception is much higher with LP652 than with LB1, that bringing about an increasing drinkability. And LB1 develops a much rounder profile with more balanced organic acid. Now, looking at this, we were really, really curious to see, okay, what is happening over here? So we did this study and comparing B134, S33, and T58. So you can see with the control, what the amount of 4VG that is present. When you compare it with LB1, you're able to see a marginal increase with the POF positive yeast strains. When we bring in LP652 into the mix, you can see that is the bright orange line here. You're able to see a drastic reduction in the amount of 4-vinyl glycol. So we thought we'd look into this. So what we were able to see is that when you compare strains like Brettanomyces bruxellensis, LP652, and a POF positive Saccharomyces cerevisiae variant diastaticus, that's what the colors stand for. Black is the Brett, burgundy is LP652, and bright orange is Saccharomyces cerevisiae variant diastaticus, which is B134, to give you an example of. You could see that in all cases, the ferrolic acid was being converted to 4Vg, especially in the bread, it was being converted to 4Eg. But when you're looking at it with LP652, there was no 4-ethyl glycol present. So we were trying to, maybe there is another pathway which is still currently being investigated by our R&D to understand what is the fate of this 4-vinyl glycol. So here what you can see is that LP652 does seem to consume some ferrolic acid during the lactic acid fermentation, and the positive character is not detected when LP652 is used for the lactic fermentation. I hope that is able to give you some idea. So just to sum up many of the points that we have discussed, you can bring about a consistent sour beer by looking at a kettle souring process, because you're able to have better control over your bacteria. The quality of the acidity produced during lactic fermentation is either through lactic acid or acetic acid. LB1 produces more acetic acid, and you can adjust this by the amount of aeration that you give your wort. LP652 also produces 2 times more lactic acid when compared to LB1, as you would have seen in the data shared by my colleague Simon. What is the flavor impact of this lactic fermentation? LB1 gives you something more aromatic and more neutral. If you would like to enhance your yeast characters, the flavor and the aroma, LB1 is a good choice. If you're looking at something where you want to enhance the citrusy, tropical, and peach character, LP652 is a really good option, but do bear in mind, it does tend to mute the phenol expression, wherein if you use it in conjunction with a POF positive yeast stream, the end product will still be POF negative. So that is just a very quick summary of everything we wanted to present. Thank you so much for your attention. If you have any questions, please do send it to the email address on the screen, that is apac@fermentis.lasaf.com. With that, Charles, Simon.
Thank you very much, Simon and Krishna. Our technical session recording will end here. Please be sure to check out other recordings on our Asia Brewers Network website and YouTube channel. And for those who are attending the live session, we'll now move on to our Q&A.